Okay, what we're going to talk about is deformation. We spent a lot of time talking about force densities, so these stresses, and that's stuff that you can't see because it's all on the inside. What we want to talk about today are things that you can see when forces are applied, and that's the deformation. So deformations take place and are accounted for in many designs. One of the most common things that we worry about is thermal deformations. So things like gaps in sidewalks and bridges, you'll see that the sidewalks have their little panels. They don't pour a whole slab of concrete because as the thermal forces cause a change in the size of the concrete, it would end up cracking. If you go and look in your basement, that typically happens. You have a large area where you pour a lot of concrete, a lot of thermal deformation. There's no place for it to expand and it cracks. At some point, I'll take some videos of my basement so you can see that. Another place would be the SR-71 Blackbird, the second coolest plane that's ever been designed by man. It is a supersonic bomber from the 60s, 70s. Sorry, not bomber, it's a spy plane. It goes Mach 3.5, I believe. The plane leaks from the ground because there's gaps everywhere. The reason that happens is because it starts going so fast, the skin friction causes the plane, which at this time I don't exactly remember exactly how long it is. I think it's 110 feet long or so. But when it starts going Mach 3, because of the air friction, it grows by 12 inches. So it's a pretty severe change in length. And so the seals and everything are set up to where it takes off on empty and then it gets in-flight refueling before it really, puts the pedal to the metal. And it's just a very fascinating design. So you'll see that constantly in designs, taking into account these deformations. So let's take a look at it. And so I apply a bar that starts at some initial length L, and it has an area of A. And so now I apply this load P, and what's going to happen is even if you can't see it, you're going to see some change in length here. And so that change in length we define as deformation. Now, on that deformation, we're using, continuing your classical Greek education, so lowercase delta. I'm sure everybody's familiar with uppercase delta, which we've used before, and so we're looking at lowercase delta. And so, that's it. That's just the geometric change that we were looking at. Now, since this is all a geometry-based change, we can play around with things. So, if I look at this as my load over my area, and so I have a change of delta. If I look at this next situation, so if I have twice the area and I apply twice the load, turns out we're going to get the same delta. And finally, if I go and I look at this one, so I have a bar that's twice as long, I have the same area, and I apply the same load, it's going to move by twice delta. So if I look at these three situations, the stress-wise anyway, stress in the first one is going to be load over the area. Stress in the second one is going to be twice the load over twice the area. The stress in this one, even though it deforms twice as much, is still the load over the area. So the entire point of all of this stuff is it's the exact same amount of stress, even though the deformation's varying slightly. So since all these cases, there's a ratio between the deformation and the length that's the exact same. So in this first one, it's deformation over length. In the second one, it's deformation over length. And the third one, it's twice the deformation over twice the length. So we see this come up a lot, this whole idea of deformation over length. And so what we're going to do is we're going to define a new parameter. And that parameter is epsilon. And actually, we're going to call this normal strain. Just like normal stress, well, this is now our normal strain. It's the strain in the normal direction. And continuing our classical Greek education, that's a lowercase epsilon. And once again, you're probably familiar with its big brother because uppercase epsilon is... Sorry, that's sigma. What am I talking about? Anyway, so we're going to define normal strain as the deformation over the length. And so that's what we're going to be doing. Now, so what are the units of strain? Well, technically it's unitless because it's going to be a unit of length over a unit of length. Customarily, we sit there and we write the units over the units even though they don't matter. So inch per inch, meter per meter, angstrom per angstrom, light year per light year. It doesn't matter what unit we put on there as long as they're the exact same unit. That comes into importance when you're dealing with things, because a lot of the time you're going to measure strain in microstrain, so times 10 to the negative 6, especially when we do our lab. And so it'll be important if you had 300 microstrain, so that's 300 micro inches per inch kind of thing. And so that's just the thing to keep in mind. But this is our equation for strain. Need to keep that in mind.